Okay, this session is being recorded from now on. Thank you very much, guys, for joining today's lab 2. In this lab, our main objective will be learn about the buck converter, how to simulate it, and how to draw and plot different graph and find out different values. So before going into the multi-sim and the simulation, let me share my screen with you and discuss the lab sheet first. Then I will take you to the NI multi-sim simulation. Share my screen. Okay. Yeah. Can you see my screen? Okay. So Kenny says yes, you can see my screen. Okay, that's good. This is the lab 2 DC-DC buck converter. So you see our main objective is to find or watching the switching waveform of buck converter. So when we are talking about the waveforms of any converter, our main objective will be look at the waveform of the inductor, capacitor, and the output side. So most of the cases, the voltage on the output side and the voltage will be same. So our main objective will be look at the current and the capacitor and the voltage and the current at the inductor. So this is a very generic circuit of buck converter where input has to be a DC voltage since it's a DC-DC converter. Then this is a diode which is just here working as a switch here, and this is the diode which is uh, usually we use Schottky diode, but normal diode will be also doing fine for that. So you can see in the basic, if I not going into deep into the equation, if I just describe you normally in the beginning, when this switch is closed, okay, so the current will be flowing through the inductor and the capacitor and the load, and by that time this diode will be turned off. So this is going to be an open circuit here, so current will flow. So this is happening when the switch is off. Switch is on here. When the switch is off, then you're going to turn it on. That means this line will be open. Then what is going to happen? This diode is going to carry the current, and inductor will be working as the source of the supplying current here. It will pass through the capacitor and the load, and it will come back through this path. So when the switch is off here, that means open, the diode is going to carrying the current and establishing the closing path for the buck converter circuit. So our laboratory work and report, they're asking you to plot the waveform for steady state cycle, IL, VL, and V out. Okay, IL, VL, and V out. So these two, and V out and VC is the same. Plot the average value of VL. So you have to plot the average value. That means there are two, because since it's a inductor, the voltage will go up and down. The plot the IL and measure the peak to peak ripple. In any converter, not only buck, it's buck, buck boost, or chook, any converter you design, the peak to peak ripple is very important, because the main objective of designing the inductor or choosing the value of the inductor and the capacitor is to minimize the ripple. So because of that, if you refer to the chapter 3, there are ripple equation for every single converter, different ripple equations. And in the ripple equations, it's connected with the value of the inductor and the capacitor. When you're going to change the value of the inductor and capacitor, the ripple will either increase or decrease. So depending on that, we have to find a suitable value of the inductor and capacitor in the simulation, then we can construct it in the hardware. When you're going to build it in the hardware, you'll find that even it is not going to 100% follow your simulation, there will be still some higher ripple in the circuit, because here when we are going to simulate, most of the cases our switching is almost like ideal. But when you are going to build it in the hardware, you'll find that this switching here, switching voltage is not going to be 100% ideal. There will be some spike in the MOSFET, or if you use IGBT, whichever you are going to use, there will be always some spike in the switch on and switch off level. So because of that, there will be a spike in the inductor current and capacitor voltage as well. So we will try our best to smooth it out by designing some advanced circuit here, but which is not part of our syllabus. If you study further power electronics in master's or PhD, you'll find that in every converter we will design some special circuit here to control the switching and switching spikes and other problems. Okay. So forget about it now. So let's concentrate here to our almost like ideal DC-DC buck converter. You have to calculate the value of the L. So you have to find the value of the L. If del IL should be 1/3 of the load current. So you have to find the load current, then you have to calculate the ripple should be 1/3 of the load current and calculate the value of the L. This is actually purely theoretical. You have to follow the equations of chapter 3. Then you have to calculate the value of the L using the given equation in chapter 3. Then verify the result by the simulation. So after finding the inductor value by calculation, you have to put the value in the circuit. Then you have to verify that your ripple is really decreased to 1/3 of the load current. Okay. Change the output power of the circuit to 1/2 of its original value. Okay, so input power and output power, you have to adjust it. Measure the peak to peak ripple IL. So when the half of power is half on the output side, you have to measure the ripple. So you can see every time we are discussing about any quantity like input voltage, output voltage, changing the parameters like power, input power and output power, we are always observing the value of the ripple, because depending on this particular ripple, the efficiency of the converter depends a lot, because if the ripple of the inductor is higher, we are going to lose a lot of power here in the inductor. And also, if the ripple is too high, you will find that our inductor is going to be switching between either continuous current mode and discontinuous current mode. Continuous current mode is when inductor or the capacitor current is staying on either positive or negative, whichever it is, it will stay to the same side. It will not cross the boundary and never touch the zero. But if it is a discontinuous current mode, you'll find that the current of the inductor will go down to zero occasionally and come back again. And in those cases, the discontinuous current mode, the power loss, it's a bit different equation, discontinuous current mode, but the value of the average inductance will be decreased and our circuit parameters and the equation will also get slightly changed. So that's why we always have to not make sure, we have to be sure that which mode we want to uh, operate our circuit. Is that a continuous current mode or discontinuous current mode? So for continuous or discontinuous current mode, we can calculate the R critical. That means the resistance, critical resistance of the whole circuit, which is related by this. So by using this equation 1, you can calculate the R critical, which is part of your problem number 7 here, or the number 7 you have to deal here. Okay, then, so let's move to our circuit. So you can see I have constructed very generic buck converter. So this is my source. I'm using an ideal switch here and operating it with a clock voltage, which is very high frequency. You can change your frequency to a different level, like 20 hertz, 20 kilohertz, 50 kilohertz, 100 kilohertz. So, but make sure if it is a DC-DC converter, usually our frequency is very high. It should be in kilohertz. It will never be in hertz. So any DC-DC converter you design, make sure that you choose a suitable frequency above 10 kilohertz. Duty cycle, I can control it from here. Okay, voltage is 5 volt, because 5 volt is sufficient to turn the switch on and off. Rising time, falling time is 1 nanosecond, because I want to make the switching is really like ideal. So it will instantly rise and instantly drop. Okay, but in real life, the rising time and falling time of the switch voltage will be usually higher, usually maybe some microsecond. So this is my switching device, which is a transistor. Okay, transistor voltage up and down, cutoff voltage is set as 5, resistance 10 ohm, and transistor off voltage is 1 mega. Okay, so this is the inductor here. Inductance is 50 micro. I can change the value later. I'll show you by changing the value how it is going to affect our converter here. So this is our capacitor. Normally in buck converter, you can see that there is a capacitor here, but in the modeling, the capacitor cannot come up with only capacitor and capacitor itself. There will be always some uh, very small level of resistor connected to every single capacitor, because there is nothing called ideal capacitor in real world. So that's why we connected a very small 5 milliohm resistor here in series with the capacitor to make sure that this capacitor behave like our real life capacitors. So there is a series capacitors connected, a series resistor connected with the capacitor. If you don't connect it, then it will behaving like an ideal capacitor, and it will give us a wrong impression about the output, because in real life in the hardware circuit we can never get any 100% ideal capacitor. There will be always some small resistance inside every single capacitor. And this is the load. We can change the value of the load, and we can also observe the output change depending on the load. Also, for the simulation purpose, we are going to use the transient simulation. For the lab one, we usually we used interactive simulation for the lab one. We bring the oscilloscope from here. Okay, that one is part of the interactive simulation when your circuit is connected to an oscilloscope outside, and you can watch the value in real time. That means whatever is happening, you can watch it directly. But for this one, we are using the transient one, because in transient analysis, we can observe what is happening in the transient level. Okay, because in real time, when the time has been passed, like few milliseconds, there is no more transient, it is already steady state. Okay, in the oscilloscope, you cannot get the transient value back in the, you cannot get the transient value, and if you want to watch it, you cannot do that. That's why we are choosing transient simulation here, so that we can observe the transient section and the steady state section at the same time. So there's an end time here. Okay. Okay. So do you have any questions so far until what I have discussed? The load current, is it IC or I out? The load current is not neither IC or not. Should be I out. IC is the capacitor current. IL is the inductor current. There is going to be a load current here, which is I out. Okay. But the voltage at the capacitor and the voltage in the resistor is the same. Okay. Okay. Let me go to the simulation circuit. Okay, just take a 1 minute break. I'll be back after 1 minute. Sorry for the interruption. My one of the baby woke up and started crying because he didn't see me. You want to say hello? See, so many people. Want to say hello? See, say they're writing hello. You want to cry? Okay, crying finish. Okay, you'll sit down, but you'll not touch anything. Okay, sit down. Don't touch anything, baby. Don't. Key. What? Touch. Okay. Okay. So let's get back to the simulation part. So here we are going to use the transient simulation. And in the output parameter, we can bring all the parameters from the circuit. So before that, it's better we give the name of our different places. So here the original net or the position name is 2. Let's give the name as input. Then you can see that inductor position, the name is L in. Okay, that's fine. So this particular node, we are going to call it L in. So what is the name of the node? This is the output node. So let's call it out or maybe output. Okay, so this voltage node will be named as a output node. This is the input node, L in and output node. So these three nodes are important to us to do the simulation. So first, let's observe the input and output of this converter. So this is 12 volt. So let's say the simulation output. I want to check the V input. Okay, why are you here? Release. Okay, V input I want to check and V output I want to check. Okay, so if you run the simulation, yeah, I can see the V input and V output. Okay, before analyzing the values, let me rerun the simulation again. Okay, let's check the duty cycle 50%. Okay, so you know that in buck converter, duty cycle is equal to V output divided by V input, which means V output is equal to duty cycle multiplied by V input. So when it is 50%, so output voltage we are expecting should be 50% of it. That means since 12 volt is our input, the output will be 6 volt. So let's re-simulate it again. Run. Okay. So you're simulating it. So you can see clearly this is the transient level and where is the transient level? So this is our transient behavior of the inductor. Output is flat. In the transient level at the beginning, the output was quite high. Then there is oscillation and there is a damping going on. So after the damping, at the steady state, it is settling down. So this particular behavior, depending on the value of the inductor and capacitor a lot, how much going to be the overshoot and how long it will take to stabilize. Depends on mainly the value of the inductor and the capacitor. So, but the steady state, it's already settled down, so that's fine. Okay, so let's put some cursor here. Cursor, yeah, cursor. So there are two cursor. Let's see, this is my cursor number 2. Let's say this is cursor number 1. So 2 output I can check. So cursor 1 will show you X1 and X2. So this is the X1 and X2 and Y1 and Y2. So if you check the V output here, so it's 5.57 and 5.58 volt. So as I told you, this is 50% duty cycle. So ideally we are expecting 6 volt on the output side, but unfortunately you can see the output voltage is 5.57. Okay. Can anyone tell why we are not getting exactly 6 volt? Any idea from anyone? potential drop from MOSFET? Not really, because MOSFET, if you look at the switching, there will be switching voltage drop definitely, MOSFET, but MOSFET switching drop will be in millivolt range, okay, and should be very small. Okay, the switching voltage is very small, which is not contributing here. Any other idea? No more suggestion. Okay, so let me play around. Mainly, this is happening because of the value of the inductor. Because although ideally, I'm saying it's ideally, right? Ideally, we assume that the duty cycle is V output over V input. Okay, but also the behavior of the inductor should be ideal, right? In an ideal inductor, we do not expect a very big fluctuation of the current, but let's look at the value of the inductor current here. Transient, look at the output. Where is our I current? L. Okay, I'm resimulating it. So let's zoom in on the current part. Can you see how big is the oscillation happening here? Is almost like from 0.6 to 1.4 ampere. So there is a big amount of oscillation going on. This is the one we call it the inductor current ripple. So the bigger the ripple is, the less ideal our DC-DC converter is going to be. Okay, but you can see from the current that still all the current is on the positive side. That means our operation is happening on continuous current mode. Okay, there is no discontinuous. If it is discontinuous, then inductor current will going down to 0. Okay, so it is still continuous current mode, but the ripple is quite high. It's approximately 0.8 to 1.4 plus. So almost like 0.6 ampere plus, it is oscillating from peak to peak. Okay, so from here you can actually measure the values from observing the curve here. And there are other ways to measure it, like if you go to the transient, I want to find the peak to peak voltage of IL buck. I have to add an expression. So you can see there are multiple expression you can put it, like the average, absolute, okay, tangent, okay, Boltzmann constant, okay, conjugate, exponential. So different parameters you can bring to find out different output from different parameters of the converter. So let's put a different value now, say make it a 10 micro. Instead of 50, I'm going to 10 micro. So let's resimulate it. Yeah. So you can see the moment I change the value of the inductor current, the inductor fluctuation is also being changed. It is now almost touching 0. So it's for momentarily it is going to discontinuous mode. Okay. Also, if you look at the output voltage, where is the output voltage? V output is 6.3370. So from 5.57, it is going into 6 volt. Right. So this one is high ripple. And also it is crossing the 6 volt, which is more than 0.50 converter circuit. So let's increase it previously it was 50, so now 10. Let's make it 1 micro. 10 times higher. Let's resimulate it. So now look at the inductor current. Hey, don't move. Sit properly. Okay. So now look at the inductor current. So you can see momentarily the inductor has going down to 0. Every single cycle, half of the cycle, almost like half of the cycle, it is conducting current, then it is falling down to 0. So it is switching back to discontinuous mode. Okay. So that's why it's important to know which mode we are operating it, continuous mode or discontinuous mode. And also you can see the output voltage is not anymore 5 volt or 6 volt. It is going to the output voltage is approximately 10 volt, 11 volt. Where is my cursor? Yeah, cursor, you can see 10.47. Okay. So see, the equation is not following at all. Like the duty cycle, you know that duty cycle D is equal to V output over V input. It's not following at all, because according to that, since our duty cycle here is 0.5, 50%. So our output voltage should be 6 volt, but you can see how largely the value of the inductor is affecting the value of our output. Okay, so let's go back to more precise values. So let's make it 12 or 13, 13. 13 should be fine. Oh no, sorry. Not 13, 13 micro. The moment I make 13 Henry, the output is falling down to 0. Okay, that means the converter is not working at all. 13 micro. Okay, so you can see a nice rectangular shape, but almost like touching the discontinuous mode. 5.78. Okay, I wanted to make it 100% ideal. Let's make it try 12 or 11, maybe 12. What is happening at 12? 5.94 volt. Okay, so almost like 6 volt. So for the value of the 12 microhenry here, okay, this particular buck converter is behaving as an ideal buck converter, which means it's 50% input and output. But at the same time, you can see that the inductor current is almost touching to the 0 point, which means giving a very high ripple. Okay, very high ripple means the power loss here will be significant. So the efficiency of the inverter is going to get compromised. So that's why, to understand the behavior and removing the inductor ripple or minimizing the inductor ripple is uh, not minimizing. Sometimes inductor ripple is important if we want to operate it in discontinuous current mode. Induction ripple, we have to accept it, and we have to induce it actually by using a different value of the inductor. So it's not about minimizing or maximizing, it's about what we are looking for. If we want to compromise the efficiency, but if you want to maintain the output exactly at theoretical value, we can do that. Or the other way around, we can come up with a less ripple. So maybe for 100 micro, the ripple will be even less. Let's try. Yeah, you can see I'm removing the ripple very low level. Okay, it's a continuous current mode 1.1.4. Okay, but the output voltage is 5.57. But the more you reduce the ripple, the behavior of the inductor is going to be better. And the inverter will be more efficient. In terms of efficiency, it will be better. So if I use 12 or 200 micro, the behavior is even good. The ripple is almost like 1.1, 1 point something to 1.2. So 1.2 peak to peak, which is very good. So that's why in the equation, where is my, yeah, you can see calculate the inductance of the value of the L if del IL, which is ripple means the peak to peak value, should be 1/3 of the load current. Okay. So this ripple value, we have to make it 1/3 of the load current. I didn't plot the load current yet, right? Okay, so let's plot the load current. Transient output, where is my load? I load, IR load. Okay. Run it. Go there. V input, I don't want to watch. V output, I don't want to watch. Okay, so maximize it. So you can see almost like you can see here. So the output current is 1.12. This is the inductor ripple. Okay, so del IL is the value from this bottom to top part, which is 1.04 to 1.2 something. So which is like 0.16. 0.16 is divided by 1.12. So some percentage, but 10%, yeah, 10%, approximately 10 to somewhere between 15 to 20 maybe, or 10 to 15%. So our ripple here is 10 to 15% here. So, but in the question here, they're asking you to design 1.1/3. 1/3 means 33%. So you have to make sure your ripple value is 1/3. That means 33%. So assuming 33% ripple, you have to choose the value of the inductor, and then you have to select that particular inductor value and show us the graph to verify that your calculation is correct and you are having 33% ripple by plotting the load current and inductor current here side by side. So, and also you have to show the calculation. You have to mark it here. What is the value? What is the value here? From the cursor, you can find out. Like if I set 2 cursor here, 1 cursor, 2 cursor. Yeah. So this is 1 to 2. You can see if I look at it, the lowest point is 1.0384, highest point is 1.19. So if you subtract it, you can find the current ripple. Okay, and IR load is almost constant. There is slightly deviation here, but almost constant. So 1.115 we can assume is the fixed value. So the total ripple divided by the IR load is the percentage of the ripple that we can find out from this graph. So that's how we design the parameters here in buck converter. Okay, now let's change the value of the capacitor and observe it. So far, if where is that? Where is my circuit? Bring all V in, V output. Okay. So zoom in, zoom in. Okay, that's fine. Okay, so this is the output. So for this 200 microhenry, our input converter is the converter inductor ripple is one of the lowest. We can make it even smoother, but no need for that now. So let's change the value of the capacitor. So 100 micro, let's make it 50 micro. 50 micro, okay. Transient output functions, run it. So first thing you look at it, when I change the value of the capacitor, let's run it here. Okay. So where is my cursor? Cursor, yeah. So you can see that it's not 6 volt anymore. The output voltage is dropped to 5.57. But you can see something. There is a certain threshold for the output voltage to get reduced. It will not go below 5.4 or 5.57, even if you choose a very different, as long as you run it at some operating condition, the deviation of the output voltage will not be very high from the ideal value. It will be somewhere between 5.5 to 6 or 5.5 to 6.2, 6.3, something like that. But if you change the operation in a very large scale, then the value is going to get really affected. But what will never happen is, this is a buck converter. So on the output side, you will never be able to get more than 12 volt. It will be always reduced voltage on the output side. Okay, so let's increase it further. Please, 100 micro, 10 micro. Let's make it 1 micro. So even smaller. Simulate it. Okay, so you can see previously it was 5.57. So now the output voltage is 5.64. Okay, you can see the inductor ripple, right? So for inductor ripple, you can see inductor ripple is changing actually quite significantly, because if you remember, it was going from 1.1 to 1.14, something like that. Now you can see the inductor ripple. So the inductor ripple is 1.19 to 1.037. So it's 0.16, slightly changed, not much. But what significant change you can see is the output current. Output current previously was almost like a DC current. Now you can see it is oscillating. It is not a AC current, but it's behaving as a sinusoidal current now because of the value of the capacitor. So it's not a very ideal value of the output current, since it is oscillating like a sinusoidal curve. Okay, so that's why the capacitor value here is going to affect the output side current. Okay, so that's why this adjusting the inductor value and the capacitor value, we have to make sure that our output is as close as possible to the input side, not the input, the theoretically duty cycle, it will follow the equation. Secondly, the output current should not have much ripple. The output ripple should be very less, because we are expecting a DC output here, since this is a DC-DC converter. So DC input output should be also DC. But you can see, depending on the value of the capacitor, the output is turning into slightly oscillating. Mama jabe? Jabe? Okay, 1 minute break. Now he wants to go to mama. Wait. Mama jabe, go. Okay, we are back again. So yeah, so you can see that the output is getting affected by the capacitor value. So let's restore it back to 100 micro. To understand the behavior, you should have a good foundation or understanding about how the equation working in the converter. That's why if you really want to know or study converter circuit in more in depth, I strongly suggest you to see the book from Erickson. Erickson is a professor. Dr. Erickson is a professor in University of Colorado. So his book is more focused on these mathematical equations and understanding the behavior of the converter from mathematical perspective. So that particular book is really helpful if you want to understand this input behavior and output behavior in terms of equations and parameters. So you can find a copy in our library, and some of his lectures are available online. So you can also look at the lectures or the lecture slides from online. So that will really help you to understand the behavior in a better way. So let's reestablish it to 100 micro, and okay, so 100 micro. So 100 micro, you can see is stabilizing our output current. So that's good, but the ripple may be a bit higher. That's also fine. So now look at the output impedance. So let's change it to 50. So instead of 5, we are increasing it to value of the 50. So let's zoom it in. Okay, everything is there. Okay, let's make it 1 point, 2 point. Okay, simulate it. Okay, in the steady state, you can see the V output is 5.56, 5.6. So when you change the value of the load here, okay, I just show you one value, right? Remember the value 5.6, 5.6 is the output value, right? Okay, previously it was 5, now 50. Let's make it 1. So I increase one time, now I'm decreasing it. Okay, where is my output? Output, come back. Okay, so output is almost intersecting here, so it's gone out. So you can see output value is 5.53, 5.53. So if you remember the previously it was 50 ohm, it was 5.6, right? Now it is 5.53. So the change in the output voltage is almost negligible because of the changing of the load. Okay, if you change the value of the load, the output voltage will not change much. But what is changing significantly is output current. Okay, since the voltage is almost constant, if you change the value of the resistor here, so the current will be significantly changed. So you can see previously current was somewhere between 1 point something or 1.1 to 1.4. Now it is definitely increased to until 6, right? 6 volt divided by 1 is almost like 6. Okay, so current is going to get affected here. So when the output current is going to get affected, you can also see that our inductor current is affected as well. So previously inductor current ripple was 1.1 to 1.2. Now it is inductor ripple is about 5.4 to 5.65. Okay, but peak to peak ripple, if you find the value of the difference here, 5 point something to 5 point what, the peak to peak ripple will be remaining same. So the threshold value will keep on changing. Okay, but the peak to peak ripple will be exactly the same. So to understand it, let's make it different values. So maybe 15. Okay, so if the resistor is 15, the current already fall down to 0 point something. So let's zoom it in. Okay, it's a milli range. Okay, 300 milli to 460 milli. Okay, so it's almost like 1.6 0.16 ampere as we found out before. So the impact on the peak to peak is almost like same as before, like 300 to 460 is 160 milli. 160 milli divided by 1000 is 0.16 ampere. So the peak to peak ripple is exactly the same, but the total current has been reduced. That means the base current is almost getting reduced. Also the inductor current, if you watch the inductor current and the output current side by side, you can see that output current is almost at the middle of the inductor. That means inductor current will always follow the output current plus the ripple, some ripple on the top and some ripple on the bottom. So if you call it top to bottom is del IL, this half we call it del IL by 2, del IL minus 2. So inductor current is output current plus del IL is the top value, and inductor current, output current minus del IL by 2 is the bottom part of the inductor current. Okay, so you can see the value of the load has an impact on our inductor current significantly, and the output current, because output current and inductor current are definitely related, because whichever current is following through the inductor, it will pass through the output as well. But the peak to peak ripple will remain constant. So which means the value of the load does not have any impact on the peak to peak ripple. And also, if you check the equation for the peak to peak ripple from your theory section, you will find that the output resistor is not part of the equation. Okay, what are the part of the equation? The frequency, the inductor value, right, and the capacitor value. But the output resistor has a very minimum impact on the ripple value of the inductor. Okay, so yeah, these are the three parameters we have to always find out: how the inductor values are impacting our circuit, capacitors are impacting our circuit, and load resistance is impacting our circuit. This one is always constant, so no need to check the input side. If you design a more ideal, non-ideal practical circuit, in those cases you have to make this MOSFET or IGBT more practical. For our case, it's behaving as a almost like ideal switch. So we are not going into that part. Our main objective is to understand the behavior of the converter from inductor perspective, capacitor perspective, and resistors perspective. So yeah, that's all about the explanation that I could have given to you. So now I believe you should be able to plot all the graph the way I show you how to plot it. Okay, so when we want to see the graph here, do not provide a graph like that. Do not provide a graph like that, because this is the place where you can provide this graph as well. But make sure that you go down to, if you want to discuss something specific, you zoom it in. Okay, you zoom in, put the cursor properly. Okay, then take the picture. Okay, also take the picture of the output side, what you want to refer, then you write the discussion. Okay, okay, so any value you want to incorporate in your report, make sure that you zoom into that particular value, capture it nicely. Okay, and also capture the output value from the cursor. That's how you can write a very good report. If this black, you can change the screen color in many ways. Show the properties, you can play around how to change the color here, and the plotting option, tracing options, so many things you can change. Okay, so whichever is suitable for your report, you choose that particular color and put it in your report. So the way I showed it, you should be able to generate all the graphs as requested here. The average value of VL, as I told you, if you want to plot the average value of VL, you have to make the transient, output side, add expression, say this is the average. VL means load, so average, then V output. Okay, so so you can see we can plot the average V output here. So also VL, the inductor, if you want to put the value of the inductor, VIL, where is VIL? This is the average value of the inductor. So if you want to put, you do the same way, add expression, average, where is VIL? VIL, yeah. So average value of VIL. For this particular lab, we are expecting you to just plot the average value of some particular thing. Nothing else, but other lab might come with different expressions. You might need to find out like RMS value, peak to peak value, or logarithmic value. But for this lab, average function is only you can use, it's fine. Calculate the IL. This is a theoretical calculation. Also, after choosing the value of the theoretical equation, you have to plot it in the multisim and find out and show that the ripple is exactly like 1/3 of the load current. Okay. Change the output power. Okay, you can plot the power as well. Transient output analysis. You can see the power, P output, PR load. Okay, P input is your input side power. P output is your output. PR load is your output side power. Okay, so you can do that. So the objective of this particular question is make the output power half of the original value. Measure the peak to peak ripple. So when the output is half, then you have to measure the peak to peak value. Okay. Yep, that's all. So I will upload this buck converter circuit for you to play around, and or you can design by yourself. Any parameter is very simple design. So I will upload it in the canvas for you to play around with the parameters and the values, and hopefully you will be able to write the report successfully. Okay. If you have any question on the lab, please you can tell me now. Any question from anyone? Nope, at the moment. Okay, so when we are going to start writing the report, I think some confusions or some question will come up. So you can ask me later about it. Also, if you want to understand the mathematics, as I told you, concentrate on the equation given in chapter 3, and also you can refer to the book of Professor Erickson. That book is quite nice. Okay, if you do not have further question, let me conclude the session for today. Okay, and this recorded lecture will be uploaded in the Canvas. So I'm not going to take any live session for the class because there is a session 2 for the lab on Thursday. If I'm not mistaken, there is Thursday. We are supposed to have another class. So that class I'm not going to take live. So this session will be work as the recorded lecture for session number 2. Okay, that will be all from my side. Thank you very much for joining the lab. If you face any problem or if you have any further question, please drop me an email. Okay, I'll try to help you as much as I can to understand the converter circuits and improve your understanding in power electronics. Thank you very much. Bye bye from me for now. Take care of yourself. Bye bye.